It is my pleasure to present today Professor Geert Leus as our distinguished speaker for the data science seminar. Professor Leus obtained his master's and PhD in EE from KU Leuven in Belgium in 1996 and 2000, respectively. After a postdoc, he then joined TU Delft in 2003, where he went over all the ranks of assistant professor, then associate, and since 2012, he's the Anthony van Leeuwenhoek full professor, sorry about the pronunciation, in the Department of EE Mathematics and Computer Science there at TU Delft. So he won the IEEE SPS, Signal Processing Society, Young Author Best Paper Award in 2002, and the IEEE SPS Best Paper Awards, not Young Author there, 2005. So like somewhere between 2002 and 2005, you crossed the threshold of not longer being a young author anymore. Right? So from that you can infer his around his age, right? So Geert's involvement with the Signal Processing Society at large is remarkable. So having served and currently serving in multiple TCs, technical committees, both in IEEE and EuroSIP, both organizations of which he's a fellow. Also on the editorial side, he has served as associate editor in various journals and as editor-in-chief for EuroSIP Journal of on Advances in Signal Processing and EuroSIP Signal Processing Journal, position that he currently holds. On the more personal side, I was lucky enough to collaborate with Geert starting back in 2015, a collaboration from which I learned a lot and quite fertile as well in terms of ideas and publications. And hopefully the best ideas are yet to come. We do have some things to continue discussing here. And then a few additional facts that you would not find in his official bio. So as a good Belgian, he's a true beer connoisseur, and he's also an avid biker, to the extreme that I feel like 1,000 years old after talking with him, and he just casually sleeping, commenting how many hundreds of kilometers he biked the previous weekend. So it's kind of embarrassing. So Geert, I know that it's quite late in Europe, but thank you for making the time to join us and give this talk. It's a pleasure to have you here, and the floor is all yours.
Thank you, Santiago, for the nice introduction. So it's really a pleasure to give this presentation here, even though it's indeed 8 p.m. here now, but I'm still very much awake, so I will do my best to give you a good presentation. Of course, I would have loved to be there in person and talk to you, but hopefully we can do that some other time. Okay, so today I'm going to talk about graph filtering, which is, let's say, an area within the field of graph signal processing, and I will start also by introducing that field a little bit. And then mainly I will focus on graph filtering for distributed optimization. Okay, so I would like to acknowledge a lot of people that collaborated with us on this topic. So not only the graph filtering part, but many other areas within the field of graph signal processing. Also Santiago is mentioned there. And I would also like to thank our funding agencies for sponsoring this work. Okay, so why signals on graphs? Why do we need them? What is the motivation behind processing those type of signals? Well, we all know that it's easy to process, let's say, audio signals and images. We all know how to do that, and video also. But those are all signals that have a very regular structure. So their domain is very structured, very regular. So in time you have the past, the future, and space you have top, down, you have left, right. So you can nicely order your domain. But what if you have data that doesn't have that type of structure? So data coming from all types of networks, for instance. I think about sensor networks where you have different sensors that measure temperature, for instance. And now you want to order these different sensors. So how do you do that? How do you order these different temperatures? You can say, okay, these sensors, they have a certain location, so I can again order them according to their location. But okay, maybe that's not the best thing to do, because okay, the temperature might not necessarily be that much related to the location. If two sensors are close, maybe they don't have the same or a similar temperature, because okay, there might be a mountain range in between, or maybe their altitude is very much different. So closeness doesn't necessarily mean that they have similar measurements. So more logical way than to order these temperatures or these sensors is by means of their similarity, right? And that can be done through a graph where the nodes are then the sensors and the edges, they indicate basically how similar these measurements are. So that could be a more logical way to order these things according to a graph, which is then very irregular in a way, but that graph then kind of regularizes or puts some structure into the domain. And okay, this graph can be learned, for instance, from historical data. Or think about transportation networks where you have the junctions, the road crossings, which are the nodes, and then you can measure, for instance, the number of vehicles that cross that junction. So that's your signal. And in that case, of course, it's logical to view these signals on top of the road network, right? Again, these signals have a spatial relationship, but it doesn't make sense to view them as being in a certain place in space, because important is how they are connected to other crossings, right? So the road network is important here as the underlying domain. Or in brain networks, if you have functional MRI time series that you measure, they are related to certain zones in the brain. Again, I could give them a spatial index, but it might be better to order them according to the brain graph, the anatomical brain graph, because you could have nodes again or zones in the brain that are very close, but that doesn't necessarily mean that these signals are related or that there's a connection, an anatomical connection in the brain that connects these zones. Or also in social networks where you have opinion profiles. So then again, how do you order these opinions? So okay, here it's obvious again that you do that according to some kind of social network, the friend network or whatever. Right, so in all these cases, we have signals on top of nodes of a graph. And we assume also that the graph is given to us. So in this talk, I assume that this graph comes from some other domain. So it's either from it's either the traffic network or the biomedical people that tell us what is the brain graph, or we know the friend network of these people, or we have some historical data that we use to estimate the graph. So here it's assumed that this graph is known. And so that is prior knowledge to us, and that can allow us to actually process these signals in a better way than classical signal processing could do that, because now we have this additional knowledge of the graph that potentially leads to better results. Right? There's also a whole area in graph signal processing. Santiago has also been working in that area, where you use data to estimate the graph, right? Topology identification. But here we assume that the graph is given to us. And you see also in all these examples here that I show that every node basically contains a time series. So that means there's also a time domain involved. So either the social, let's say the opinion profile changes over time, or the temperature changes over time. So actually, these examples that I showed you here, they have two domains. You have the graph domain, but also the time domain. But since we know how to handle time domain, I will make abstraction of that here. So I assume that we have just a single scalar value per node in this talk, because our interest here is to talk about the graph domain and not the time domain. Of course, there's a lot of research out there where these two domains are jointly handled. Okay, so let's make it a little bit more concrete. So we have our support of the signal. So it's represented by means of a graph G. So it has a set of nodes V, capital N nodes, and we have a set of edges E, so capital M edges. And the structure of the graph is represented by means of this adjacency matrix. In what way? Well, suppose that you have an undirected edge here between node 2 and node N. That means that we have two non-zero entries in the adjacency matrix at row 2 and column N, or at row N and column 2. So undirected graph here, undirected edge, sorry, has no arrows here. But if you consider here a directed edge between V1 and V3, then we only have one non-zero entry in the adjacency at row 3 and column 1. And the entry at row 1 and column 3 will be 0. And the weight of these values is basically the weight then of this edge, which I depict here by means of the thickness of the arrow. Right? So the adjacency matrix kind of encodes that structure, the whole domain in a way. And then on top of that graph, we have our graph signal, right? So the nodes are connected to scalar values. So as I mentioned, we assume a single scalar value per node, and we stack them into this vector x. And here we assume that all these values are real. Also, the weights, we assumed that they were real and positive. You can extend these things to negative weights and even to complex valued signals, but to keep things simple here, we assume everything is real valued. So the vertical bars here, that's your signal on top of the graph. And then you could say, okay, how do I order this now? Is it important how I order things? Well, it's not so important. As long as the ordering here of your signal is the same as the ordering in your adjacency matrix, then things are fine. And it doesn't matter how you order things. Of course, if I would do regular processing using a classical DFT operation, a Fourier transform, then of course it matters how I stack things into a vector. But since now I connect X to the domain A, as long as I make sure that these two orderings are aligned, then it's fine. Okay, so I told you that this adjacency matrix kind of captures the structure of the graph, but there's many other matrices that can do that. It's also the graph Laplacian or modifications even of the adjacency matrix or the Laplacian. And we want to make abstraction of that, so we just talk about the graph shift operator, and why we call it graph shift, that will become clear later on. So we will use this operator S here, which will depict basically, which will be the matrix that represents the structure of the graph. So it will be only non-zero if we have an edge, basically, and that's related to that entry in the shift operator or on the diagonal. So it depends whether we have a non-zero value on the diagonal or not, depending on the type of graph shift operator that we have. So it could be that it's the adjacency matrix, but it could also be that we use the Laplacian, which is then the degree matrix minus the adjacency. It's not so important here what exactly that we're using. So some research group, they prefer to use the adjacency matrix, others the Laplacian. Here for the Laplacian, very often we assume that we have a symmetric matrix, so we have an undirected graph, but you can even define Laplacians also for directed graphs. The nice thing about the Laplacian is that there's some kind of notion of smoothness. So if you look at this quadratic form here of your signal with the Laplacian, that this is nothing else than kind of a weighted sum of squared differences of your signals over the edges. So the weights here are your edge weights. So if this value is small, it means that the signal values over edges are very similar. So you have a smooth signal over the graph. But you also have a similar smoothness measures for the adjacency matrix as well. So then it's more related to total variation. I didn't write it down here. But for both the adjacency and the Laplacian, there are notions of smoothness and hence notions of frequency in a way. So if I order signals according to smoothness, then you could say that these signals have different frequencies on top of this graph. And the way to reveal these different frequency modes of a certain shift operator is by means of an eigenvalue decomposition. So if I take an eigenvalue decomposition of this shift operator, then it turns out that these eigenvectors here in the U matrix, that they represent kind of the frequency modes, and you can order them according to the smoothness. Either for the Laplacian, if your shift operator is Laplacian, it will be this smoothness measure. If it's the adjacency matrix, your shift operator, there will be another total variation type of smoothness measure along which you can order these different frequency modes. Here we also, for simplicity, assume that S is a normal matrix, so that our eigenvectors are orthonormal vectors, but it's possible to extend this as well, right? So I'm not going to go into details of the whole frequency domain analysis of graph signal processing, but just remember that, okay, these eigenvectors of the shift operator, they represent the different frequency modes. So that's an extension of the DFT vectors, what you have in time domain. You can also show that if S is a simple delay operator, that then the U is, of course, obviously the DFT matrix, so the classical frequency modes. So this is a valid extension of let's say, processing on the time domain, an extension towards the graph domain. And of course, if we know how to reveal different frequency modes, we can also start spectrally shaping the signals according to these different frequency modes, right? So we basically, this U matrix that I showed before defines a so-called graph Fourier transform. So I can project a signal on these different frequency modes, and then I get this new signal x hat, which will be the graph Fourier domain representation of your signal. And I can do, of course, the inverse operation. Right, so and if I can define this graph Fourier domain, I can also start modifying the frequency content of my graph signal, right? So I can magnify certain frequencies and attenuate other frequencies. And I do that just element-wise by an element-wise product, right? If we look at the end frequency component of my graph signal, I can multiply this with a scalar value. For instance, we set it equal to 1 to keep that mode, or we set it to 0 if we want to suppress that mode. You see a picture here where you have the different frequency modes, and you can have this red graph filter that kind of only keeps these modes here and suppresses all the high frequency modes, for instance. And we represent that by means of a function h of lambda n. So lambda n are the different eigenvalues of the shift operator. So those are also called our graph frequencies then. So the eigenvectors are these frequency modes, and these eigenvalues are our graph frequencies. And I can stack that into a matrix vector product. So we have actually a diagonal matrix times our frequency domain representation of the signal. So this is, let's say, what we have also in time domain. So if we do temporal processing, then also how do we do filtering? Well, we just multiply in the frequency domain our signal vector with the diagonal matrix. And on that diagonal, we have the frequency response of the filter. So in frequency domain, this is just an element-wise product. So how does it look like now back in the vertex domain, in the node domain? So then we get this operation here. So the U Hermitian brings you to the frequency domain. Then you have your diagonal operation, and then you go back to your vertex domain. So you see that actually this filtering, this suppressing or magnifying of frequency modes is nothing else than, let's say, this matrix vector product here. So it's a linear operator H, but it's not any linear operator. The H matrix here should be diagonalizable by means of the graph Fourier transform, this U matrix, right? So then it's an eligible graph filter, if that's the case. And that's also the same equivalent to saying that it has this shift invariance property, where if I first apply the shift or then the matrix H, it's the same as first applying the filter and then the shift. Right? So this is, let's say, an extension of the classical LTI, linear time invariant systems, but to the graph domain. So these two are basically equivalent. Now you can say, okay, that's nice. So we have this kind of graph filter. So where can we use these things? So one application of graph filters is interpolation. Suppose that you have this sensor network that I showed you before, and you have the blue sensors. They can measure something, but you have some kind of malfunctioning sensors, so these red sensors. But you still want to infer the signal on these sensors. So how do you do that? Well, you basically look a bit at your neighbors and you take some kind of an average, right? But the mathematically rigorous way to do that is by designing basically a low-pass graph filter, which implicitly is going to take some average of your neighborhood, but it does it in a kind of a rigorous way. So this also appears in semi-supervised learning, right, where your graph is determined by your features, and then you have the graph signal itself are the labels on these nodes, and then for some of the nodes we don't have a label, and we try to interpolate these labels. So this also fits to this semi-supervised learning application. You can also do denoising of the signals, but taking the graph structure into account. So suppose that you have this kind of community graph, different communities. So you have lots of connections within a community, less connections between communities. And suppose that they have, let's say, a certain signal value within these communities, but there's some perturbation and you want to do a denoising. But I don't want to get leakage from one community in the other one. So I want to only do a smoothing within the communities. Well, a graph filter is going to do that automatically, at least a low-pass graph filter. So at the end, so you remove perturbations within a community, but you don't get leakage of the red color into the blue, for instance, here. Also in image processing, this is being used, this type of graphical denoising. Another application is graph convolutional neural networks. We all know that convolutional networks or neural networks are very popular in audio and image processing, where you have different layers, and in between layers we do convolutions. But these are convolutions in time or in space. And again, these are convolutions in a very nicely structured domain. if you now want to classify, let's say, signals that don't have this nice regular structure, like authorship attributions or something like that. So you have basically different books or different pieces of text which have no regular structure. So how do I do a convolution on a text, right? Or on a social network? Right? And basically, this graph filter gives you a definition of how to do a convolution. So what I showed you before, so this can be viewed as some type of convolution, but a convolution on a graph. Right? So we can use this type of operation in between layers in then a so-called graph convolutional network to do classification, but classification of graph signals, of signals on graphs, or maybe also of certain nodes within a graph. Right? So I'm not going to talk about today. So this is very interesting, but today I'm going to take it one step back in a way and see how it also can be used in distributed optimization. We will see that there are connections between the two, but so I will apply this to distributed optimization, where we have different nodes that have different objective functions, and we want to minimize a superposition of these different objective functions, but without fusion centers. So we assume in this case that the graph is like a communication graph that can exchange information. Now, and we will show later on how graph filters can be used to solve that. Okay, a little bit about graph filter design and implementation. So I showed you how it looks like. So this is basically how it looks like in the vertex domain. So we have just a linear operator that is diagonalizable by the graph Fourier transform, and that also has this kind of shift invariance property. So first, how do you implement that, right? We know from the temporal processing that it's useful to implement things in the Fourier domain. Right? So we take a fast Fourier transform, and then we just have an element-wise product. Because this diagonal matrix here is very easy to implement. It's just the order of magnitude equal to the number of nodes, so capital N. The problem, though, is that there's no fast implementation of the graph Fourier transform, at least not for general graphs. So in this graph signal processing, it might not be so useful to do the processing in the frequency domain, because we still have to do a full-blown matrix vector product here when we go from one domain to the other. So then it's better to directly do this matrix vector product in the vertex domain. But even that one, it's still a quadratic complexity in the number of nodes. So if you have graphs of millions of nodes, this is still a huge operation. So that's why in this field of graph filtering, people are looking at parameterizing H in some way that this H times X can be efficiently implemented and potentially also distributed in a distributed manner. And that's what we will see later on. How can I parameterize this kind of H matrix such that it's still an eligible graph filter, so it's still diagonalizable by the graph Fourier transform, but so that I can implement this in a more efficient way. What about the design then? So we have now this kind of parameterized form. So this parameterized form can either be written in the frequency domain or in the vertex domain itself. So this capital theta here contains the parameters. Later on, we will see how we can actually parameterize this. But just on a high level, how do you do then the design? Well, you can do the design in the frequency domain. Suppose that I give you a certain desired frequency response, like you have also in temporal filter design. So you have an ideal low pass filter, for instance, or an exponentially behaving low pass filter. So how do you try to find a set of parameters such that this parameterized filter is close to your desired filter? And I can do the same in the vertex domain. Now, the interesting thing is about the frequency domain that you can do it in two different ways, either knowing the graph or knowing the graph frequencies. So then you get this kind of red design. So suppose you have a 6-node graph and you know the graph frequencies, so lambda 1 up to lambda 6. In that case, I can just do this kind of approximation here just for the relevant graph frequencies of that graph. But of course, that means that you have to know the graph and you have to compute the eigenvalue decomposition in order to figure out what are these lambdas, what are these different graph frequencies. Of course, if you have a huge graph, this is again very complicated to do. So that's why people also have been looking at graph independent designs, or so-called universal designs, where I do this fitting, but over a continuous range of graph frequencies. So I just assume that I know the minimal value of lambda and the maximum, so I have a certain range, and then I do the fitting using this blue curve, for instance, again using the same parameterization, but I do the fitting over a continuous domain. And there's many designs that are related to that. I'm not going to go into details here because that's not the focus of the talk, but so there's many methods graph dependent, and many methods graph independent. Of course, the vertex domain fitting, if you do that implicitly, you kind of have to know the graph. So that one is always kind of graph dependent. You might not have to do, though, the eigenvalue decomposition here. So that's still an advantage then of this design. Okay, so what is one of these parameterizations? Well, a very popular one is to parameterize this H matrix in terms of a matrix polynomial. So it's just a weighted superposition of different powers of the shift operator, right? And we apply that to a graph signal. Now, is this an eligible filter? Well, yes, because we know that the shift operator, by definition, is diagonalizable by the graph Fourier transform, because those are the eigenvectors of S. And then powers automatically will also be diagonalizable by the graph Fourier transform, and then this weighted superposition is also like that. So it is an eligible graph filter, and the frequency response is nothing else than this kind of polynomial in the graph frequencies. So if we think about this fitting here before, if we want to do a fitting in the frequency domain for this type of graph filter, we have to do kind of a polynomial fitting, right? And we can do that either based on given graph frequencies or by a continuous range of graph frequencies. Now, is this now a good parameterization? Well, we see later on that this can also be that this H times X, this H FIR times X, can be easily implemented efficiently and even in a distributed manner. But we will come back to that in a second. Okay, so why do we call this actually finite impulse response graph filter? We call this FIR graph filters. Well, it's clear that if you replace your S by a simple delay, right, that you get your classical temporal FIR filter, right? That's also represented here in this slide. So we do shifted graph signals here, different powers of S that we multiply with X. Well, we can actually view this in time domain as time delaying your signal. And then the weighted superposition of different time delayed signals, we do that also in the graph domain. We have a weighted superposition of this graph shifted signals. So in case my shift operator is a delay, I basically get my classical temporal FIR filter, right? So this is kind of an extension of an FIR filter to the graph domain. And both of them kind of carry the notion of a convolution. It's kind of a shift and sum operation. And that's also why we call this as a shift operator, because it appears as a shift operator in these kind of FIR graph filters. And of course, this is, as I mentioned, important in these convolutional neural networks where we want to find, let's say, an extension of the convolution operation, but to the graph domain. So now, okay, let me now illustrate why this is easy to implement. So suppose that we have a second order graph filter. So then we have these three terms here, right? Phi 0x, phi 1 sx, and phi 2 s squared x. So how do we implement that? Well, the first term is very simple, right? If we look at the ith node, so the ith node just takes its initial value, so xi, and we use superscript 0 then on top of that to indicate that this is the first value, and just multiplies it with phi 0, right? And that gives me then the first term of the output for node I. What about the second term? So there we have sx. Now, how do we compute sx? Well, for node I can very easily compute its value for s times x, because it just has to ask the latest value from its neighbors, and those are the values with superscript 0. And then it has to take a weighted superposition with as weights the related entries in this shift operator, and that gives this node I its shifted output. And that one I multiply with phi 1, and that will give me the second term here in the output for node I. The same for the third term. I just do the same thing again. I just multiply the previous result with s again. So multiplying with s always means that every node just has to look at its neighborhood, asks the latest values, and combines that using the related entries in the shift operator. And that gives me these outputs for node I for these different shifts. So we have kind of a diffusion operation here, which is very simple to implement. So basically, it's what I write here. So it's an efficient implementation, and it can be distributed. So every node I can do that by itself, just talking to its neighbors without even knowing the full graph. So the total cost is how much then? Well, every node basically has to talk capital K, which is the order. So it has to talk capital K times to its neighbors. So that depends, of course, on the degree, but the total number of edges will be then the number of times that all the nodes have to talk to each other. So order of magnitude will be the number of edges times the filter order, capital K. So that's here the cost now. So compare this to the original cost that we have, where you multiply h with x itself. So in that case, we had quadratic complexity in the number of nodes. Now we have this complexity here, number of edges times the order which is usually very small, at least much smaller than the number of nodes. And so if the degree is kind of fixed for all the nodes, then here this complexity is like linear in the number of nodes. So we go from quadratic to linear in the number of nodes. What's also interesting later on for the design is that this parameterization here is a linear parameterization in these scalar weights phi sub k. Now I told you also that this is kind of a polynomial matrix in the matrix shift operator S. So if you do the graph design, the graph filter design in the frequency domain, you get this polynomial in your graph frequencies. So if we want to do the fitting there, it's basically polynomial fitting. And we know that polynomial fitting is not very well conditioned in general. So that's why we have to restrict our capital K to low orders in order to get a well-conditioned filter design problem. But if I want to, on the other hand, get a good approximation of my fitting, I need a high filter order. So there's kind of a contradiction here. So I need high filter orders, but then the problem gets ill-conditioned. So that's why in the past, we have also been working on IIR filters, which is also an extension of the temporal IIR filters, but to the graph domain. And in those cases, we can get much sharper filters for a smaller order. But again, I'm not going to talk about this here, but all the things that I will later on discuss can also be extended to this infinite impulse response or so-called autoregressive moving average type of filters, but for the graph domain. Okay, so this is the FIR filter, so which is diagonalizable by the graph Fourier transform. So now can we also think about other types of filtering operations that kind of extend this operation? If we think about this now, so we have this kind of diffusion, and then for every node we combine these outputs for the diffusion with these constant weights phi 0, phi 1, and phi 2. But here you can already see that, okay, why do we make this node independent? So what if we now change these filter weights depending on the node? So for node I, we do another combination than for node I plus 1, for instance. And then you get a so-called node varying graph filter. So in that case, we run the same diffusion again. So again, every node talks to its neighbors and the information is exchanged. But then when a node combines its results, it uses its own filter weights. So that's kind of an extension of let's say a time varying filter in the time domain to the graph domain. So this is one possible extension of time varying temporal filters. And complexity wise, nothing really changes, right? Because the complexity is the same as before. It's just we use a different set of weights here for every node. And in the total filter, in the filter structure, the fact that we use different coefficients for different nodes, that appears here now as a diagonal matrix. On the diagonal, you get the different filter weights for the different nodes. So we get this diagonal operations here now. We get diagonal matrices instead of scalars. But again, it's a linear parameterization. So later on for the design, that's important. So it's just a linear parameterization. And clearly, if the elements on this diagonal are all the same, then we get our classical FIR filter back. But it's a linear parameterization. That's important. We can even take it one step further, right? We can say, okay, we run here this diffusion, and this diffusion always uses the same shift operator S. But what now if we run this diffusion with different shift operators? So in every diffusion step, suppose that we use a different shift operator. So first we use phi 1, then phi 2, and then phi 3. Of course, we assume that these shift operators still have the same support as the original graph, but the weights are different. So the weights will be different than the weights in my original shift operator S. So they might be different than actually the similarity between these nodes, which you have in your adjacency matrix. And we also include the diagonal term here. So these phi matrices, these diffusion matrices, they might also contain a diagonal. That's also why the first term is not just x. So that's why the first term is already phi1 times x, because we can omit this term that is just containing x because it's included in this product. So that's what we have here. So the first term is phi1 times x. So a node talks to its neighbors. It asks for the latest results, which have index 0, and then it combines things. It combines these results using the weights in this new shift operator. And we use that different shift operators for different diffusion steps. And then in the end, we just superimpose all these results. We don't have to use any weights here anymore because they can again be included in these new shift operators. So now we get this expression for our H matrix for our filter. Again, this is not a shift invariant filter. So this is again another extension of time varying filters to the graph domain. So those are not LTI systems anymore, like the node varying filters. But again, the implementation is the same as before. So it's very efficient again. It can be distributed. We only have to change here the weights that we have in these diffusion steps, and that's it. And we have no more weights here when we superimpose these results. So again, the computational and communication cost is order of magnitude capital N times capital K. So again, linear in the number of nodes if the degree is fixed. And this again specializes also to the classical and the node varying graph filter. So this is kind of the most general type of graph filter that you can think of that operates over the edges of the graph. Of course, the problem here is that it's not a nice linear parameterization anymore in the coefficients. First of all, we have matrix coefficients now, so there's a lot of coefficients, but it's not linear anymore in those. So although there are ways to design this, it's kind of complicated now to design such filters because you get this kind of highly non-convex optimization problem there. So we looked for a solution to that, and then we came up with these constrained edge varying graph filters. So there we still run our original diffusion with a shift operator S, but before summing the results, we do another shift operator. So on X, we do the operation phi1 times X. So on Sx, we apply the shift operator phi2, and on S squared X, we apply the shift operator phi3. So we run actually our original diffusion like we did in the classical filter and in the node varying filter. But then before adding them together, we run another diffusion step with the matrix that we then optimize. So that's these phi matrices, which again have the same support as the original graph, of course, right? And then you superimpose these results. So this is kind of somewhere in between, you could say, a node varying and an edge varying. But now the interesting thing is that we have a linear parameterization in these phi matrices. Okay, we still have a lot of coefficients, but at least we have a linear parameterization which will simplify the design. And the implementation is again efficient and distributed, so it's a little bit larger than what we had before because we have to run now maybe 2 diffusion steps, but still order of magnitude is a number of edges times order of the filter. And this again, actually this simpler case also specializes to the classical and the node varying graph filter. So it's still a more general class of graph filters than the ones that were developed. But it's less general, let's say, than the full-blown edge varying graph filter, but it's a linear parameterization, so that's why we like it. So now how do we design these filters? So I told you we like these linear parameterizations, so that's what we have here. So this can now either be the classical filter or the node varying or this constrained edge varying. So all linear parameterizations, either in the scalar values, in the vector coefficients, or in these matrix coefficients. But it's linear, so I can simply solve a least squares problem if I know my desired response. Right? So in that sense, it's a simple design. So here we do the design so this is a vertex domain. You could also, at least for the classical filter, you could consider a frequency domain design. Of course, the other filters, the node varying and the constrained edge varying, since they are not shift invariant, there's no frequency domain interpretation for those. That's why we stick here to the node domain design. Also, if you think about machine learning and you don't have your desired response, but you just have input-output relationships, then I could also basically try to fit this parameterized filter to the input-output data. So instead of solving this least squares problem, I could solve this kind of data-driven least squares problem, where I have input-output data given to me. And if we apply this to, let's say, some desired responses, which could be an exponential graph kernel, which is used, for instance, in clustering, or an ideal low-pass filter, which is used, for instance, in denoising. If we then look at the error, so the fitting error, then we see indeed, as expected, that for the classical filter, depending on the filter order, so it goes down, but we get it goes down slowly. So if you look at the green curve, so the node varying filter goes down much more quickly, and the constraint edge varying even goes faster. Also for this ideal low pass filter here, you see also some kind of saturation effect, which is also a bit due to the fact that we still have polynomial forms. So the fitting at very high orders becomes always a little bit ill-conditioned. We will come back to that later on. But you see that, okay, there's an advantage of this constraint edge varying over the other ones. So for the same filter order, we get much better results. Or for a particular error that you want to achieve, you can reduce the filter order and hence the complexity a lot. Okay, now how can we use this for distributed optimization? So again, what do we do in distributed optimization? So we have these different nodes, and these nodes are related to a certain local objective function that you have. And we want to minimize the superposition of these different local objective functions. And you want to do that using data exchanges over these edges. So in this case, the edges are not necessarily related to similarity of the data or something like that. Here it's a pure, let's say, communication network. So these are communication links that are available to you. And okay, we know that, okay, data exchanges that can be somehow viewed as diffusions over a graph. So we will diffuse some kind of information over this graph. So that's why there might be a link with graph filtering. Okay, so here particularly, actually, we consider optimization problems where these functions are also parameterized by some input data. So every function is given some input data. So that's actually our graph signal, y, our input graph signal. It could be that the node I only gets one component. It could be that it gets the full vector. We will see some applications in a second. That's not so important. What is also important is that we kind of know what is the solution of this problem. So we assume that the solution is a linear transformation. So we consider very quadratic type of optimization problems where the solution is just a linear operation on the input data y. We can extend it to, if you have a data-driven approach, I will tell you later on how you can think of extending this to more general approaches where this solution can be computed, but it's not necessarily, let's say, a linear transformation of your input data. But for now, let's assume that we know the global solution and it's this linear transformation. If we know that this is the case, then okay, yeah. So first some applications. So think about average consensus, for instance, where you have different agents and they have a value yi, and you want to find the average, right? So you kind of minimize this kind of superposition of local cost functions. So this fits this kind of design problem. Or think about distributed imaging. So you have a radio astronomy image and you have different antennas, and the antenna observes the image X, but through this linear operation GI transpose. So in this case also, it's kind of a linear least squares problem, but that you have to solve in a distributed fashion. Or think about distributed beamforming. So you throw out some sensor nodes, and they every node wants to compute, let's say, the beamforming output by directing the whole network into a certain direction. So here the W Hermitian, every row of W Hermitian is a related beamformer that a node wants to compute. Right, so here we actually already know the global solution. So if you want to write this as an optimization problem, you actually have to introduce the pseudo-inverse here in your problem. So we don't like, actually, if we already have the solution, we don't want to write it like that, but just to couple it also to distributed optimization. All these type of problems can be written as a kind of a distributed least squares problem, and their global solution is actually just a linear transformation. So if we have this kind of global operation, it's now easy to think of approximating this global operation by means of graph filters, because we know that they can be implemented in a distributed fashion by just talking to my neighbors. And we know that the complexity is the number of edges times the order of the filter. So if you can keep the order low, in approximating this H tilde, then we have a low complexity implementation and a very fast one, because the order is basically the runtime then of that adaptive algorithm to converge to the solution. So if the order is low, we have a very fast convergence. So we just do that fitting, right? We know the global operation and we fit a graph filter to it. It can be a classical one, or the node varying, or the edge varying, or the constrained edge varying, whatever you want to implement. So as I mentioned, so this only works if the solution is linear. Of course, you can follow a data-driven approach, as I mentioned, and then the solution doesn't have to be linear. You just fit input-output data. But remember that, of course, the model that we have is a linear model. The other thing that you have to keep in mind is that this design either has to be done by some kind of fusion center, and then the fusion center has to tell the different nodes what are the weights that they have to use to talk to their neighbors. So in that sense, for the design itself, there has to be a fusion center. Or alternatively, the nodes themselves, they all carry out the same filter design, but that means that every node has to know the full structure of the graph, and every node also has to know this global operation, right? So those are two kind of assumptions that are different in this framework compared to traditional convex optimization or distributed optimization, where nodes generally don't know what is the global structure of the graph and or the global operation. And that's why we can potentially do better than classical distributed optimization methods like ADMM or so. So some applications. So let's think of a very simple average consensus problem. So we have our consensus matrix. So it's all one matrix in that case. So there, the global operation is well known, and it's just an all one matrix divided by n. And then we just fit different filters to it. So either a classical one, or node varying, or the constrained edge varying. And you see that with the constrained edge varying, that after talking, let's say, 7 times or 6 times to my neighbors, I kind of find the solution. I find the average consensus, which makes sense. So for such a graph in a community setting, after 7 rounds, I might have reached my neighborhood. In distributed imaging, so again, so you can follow a distributed least squares approach using ADMM or the primal dual method of multipliers. So that's one option to do it. The other option is that you use the global solution. So we know that the global solution is the pseudo-inverse, is given by G pseudo-inverse. So that means that every node actually wants to apply this kind of wants to apply a column of the G pseudo-inverse transpose to the output data. So if a certain node wants to know the first pixel, it has to apply this G tilde 1 to the output data, to the measured data Y. Right? And if it wants to know the second pixel, it has to apply the G tilde 2 towards to the vector Y. So basically every node has to apply all these filters, and that's why we need actually one graph filter per pixel. And then we have to implement this kind of rank 1 matrix here. So that will be the optimal global operation, where every node will figure out what is pixel I. So this is the filter related to pixel I. And the fact that we have an all one vector in front of it means that all the nodes want to actually apply this operation. So that's why for every pixel we have a design problem like this, and we will get a graph filter for every pixel. And if we compare this to, let's say, a PDMM, which is this the red curve, so you see that the classical distributed convex optimization method goes down, so it converges, but it goes very slowly, right? If we look at our methods, so the constrained edge varying and the node varying, so the blue and the green here, so they converge very quickly, but you see that they saturate at some point, right? And that's because of the polynomial ill conditioning. That is an issue, but we will see later on that we can solve that. But at least for a low number of iterations, we can do much better than classical optimization, distributed optimization method. And that's because we use this assumption that the nodes know the structure of the graph and they know what is the global operator, which the classical ADMM or PDMM, they don't have that information. Also distributed beamforming, so assume that you spread out these sensors and they want to implement this kind of beamforming operation where you have W Hermitian times Y. So every row of W Hermitian is basically a beamformer that you want to implement. So suppose that every node wants to look in a different direction. So then every node has a different row in W Hermitian. Okay, the distributed optimization approach has to use kind of this pseudo inverse here, but we can directly fit the graph filter to this W Hermitian then, right? Because then this graph filter will actually implement this filter operation where every node looks or applies a different beamformer. Right, and we can see here if the desired beam pattern is here given by this green dashed curve. We see in blue, that's the obtained pattern from an edge varying. This is a constrained edge varying graph filter that comes very close. You see the node varying doesn't do so well. The classical graph filter would not do very good here. So you really need these kind of extensions of this classical filter to obtain a good result. Okay, to wrap up, maybe very quickly on how to deal with large filter orders. So I told you here, especially it was especially visible here in this distributed least squares. So we have the saturation at very large filter orders because of this ill conditioning. So that is kind of an issue that we wanted to solve. And one way to solve it could be to say, okay, I stop after 10 iterations, I stop, and then I start running maybe a classical distributed optimization approach. So that's one way. But another way was to view these higher order filters as a concatenation of small order filters. So we try to view these large order filters as a cascade of smaller order filters. That's how we try to tackle this problem here, right? So we try to write our filter as a product, so a cascade of short order filters, because we know that they can be easily implemented and designed. So let's then concatenate different of these filters. And this, of course, starts looking like a multi-perceptron neural network, right? Where in every layer you have a different short order filter. Of course, we don't have non-linearities in between, but potentially you could put a non-linearity after every filter output, and then you basically get a graphical neural network. But here since we want to fit linear operators, we just consider a product of short order filters. So here's the structure. So this is for the constrained edge varying graph filter. So this is one graph filter. So you run your regular diffusion, and then you have your diffusion steps, phi1 here after the first order, phi2 after the second, and so on. And you concatenate many of these filters in a series. And we hope that this improves the conditioning and that we can get a better fit with reduced order filters. Of course, now the design becomes, again, very highly non-convex and non-linear, right? So it's not a linear least squares design anymore. So that's why we try to look at some algorithms to implement this. One way could be to use classical backpropagation learners like Adam or something to even learn the parameters, the weights in this structure. Okay, there's no non-linearity, but you can use actually similar tools. We were looking at some kind of sequential fitting where actually we split our cascade into a left filter and a right filter and a middle part. And we will basically, so we do that because if we fix everything except for the left filter, then we get a very sparse least squares problem. Or if we fit everything except for the right filter, we also get a sparse least squares problem. If we have to estimate the middle one, we get a non-sparse least squares problem. So that becomes a huge problem. So that's why we only want to do a sequential fitting of left and right. And we do that starting with a very low order. So we start with order 1, and then we fit left and right. And then, a low order of number of cascades. So that is capital Q. So we start with, let's say, 2 cascades, 2 filters, and we optimize HL and HR, and then we increase we add one more cascade. Again, we optimize inner and outer, and we increase Q in that way. So that's the approach that we follow. So I'm going to skip the details of this method. So it's kind of a borrowing ideas from this relaxed method where you kind of do this iterative fitting up to convergence, and then you add one more filter to the cascade, and you repeat the whole thing. And these estimating these HR and HL values are easy to do because of their sparsity. So you have this routine lin sparse solve that solves these left and right ones up to convergence, and then you add another filter to the cascade. And that's the whole algorithm is then this kind of right-left iterative fitting procedure. So again, I'm going to skip the details. So just to show you this result where we applied this for consensus, this was over a network of 500 nodes. So again, a very simple distributed least squares problem in a way. So if you look at what the classical optimization, the convergence of a classical distributed optimization tool, such as this primal dual method of multipliers, so you see that it goes very slowly. So 60 iterations, nothing has happened. But if you look at this cascade of the constraint edge-varying graph filters, then we are already at machine precision here. So after 35 steps, we are basically there where we have to be. Right? So it's super fast compared to traditional methods. Of course, the prior information is different, so it's logical that we potentially could do better. But yeah, so this clearly solves the problem of the saturation effect. So this is the fact that we have a saturation here is just a numerical precision. So the node varying does not so well. It does a little bit better than the classical, but you really have to go to these edge varying filters to obtain this kind of result. Okay, so with that, I want to wrap up. So I gave a kind of short introduction of the field of graph signal processing. Then I introduced graph filtering, where you can use that. And then we have discussed this also, how you can use these graph filters for distributed optimization. Of course, as I mentioned, we do it here for linear transformation and data independent, but you can add non-linearities and you can do it data driven, and then you basically can do the fitting with graphical neural networks. But this is, let's say, the starting point where things are linear. So with that, I would like to conclude, and so I'm happy to take any questions that you have.
Great, thank you. Thanks a lot, Geert, for the presentation. So yeah, so feel free. Everyone can write their questions in the Q&A box. In the meantime, while people are thinking, let me just start myself, just to get the ball rolling. So actually, with this last point, maybe we can take it from there. So, so what would you say that there are like lessons to be learned from this linear fitting of graph filters, or the cascades, and things that we could translate, if anything, to GNNs, right? And then graph neural networks. And then do you think that something like this would allow us to get good optimizations for deeper GNNs that sometimes we can think that they don't work too well if you go deeper? Do you think that part of it is in the optimization, or there's something more fundamental?
Yeah, that's a good point. I don't, to be honest, it's hard. It's a hard question also, but
it wasn't the easiest one to start with.
Yeah. Actually, the nonlinearities sometimes help also in solving it. Actually, solving this, so solving the fact that you have this linear cascade without nonlinearities is harder to optimize than when you have these nonlinearities, because things grow out of bounds much more easily. Mm-hmm. So actually, the nonlinearity might help there just to do the design. So this might be even harder to design than the graphical convolutional neural network. So I don't think we can go very deep here. Maybe we can go less deep here than in the graphical neural networks. I actually don't know for these ones how deep, what were the size of the filters here. So this is not Q, so this is the total filter order, but I don't know how long. I think the filters were relatively short here. Mm-hmm. So 30 rounds might mean that you have, let's say, 6 cascades of order 5 filters or something like that.
I see. Okay, cool.
But it's it's a good. But I don't know if there's lessons, if you can learn something from this for the nonlinear case.
Good. So the other one is, so sometimes you show these plots, of performance as a function of k, or of number of communications. So if one would look at performance as a function of number of parameters, right? Because of course the edge varying thing for a given number of communications has more parameters. So, do you have an idea how would something like that look like? Like performance number? Yeah, how would they compare? Is it also clear cut? Like here is very clear cut, right? But
of course here we don't have, let's say, an issue of too little training data, right? Because we do a direct operator fitting, right? So we know the operator. So this is not data driven. So I don't need even training examples here, right? So in that sense, the fact I cannot over parameterize things in a way. So the fact that I have more parameters is not such a big deal here. Of course, if this would be data driven, then it's another story, right? So then it might make sense maybe to plot versus the number of parameters, and also versus the number of training data that you have, and there will be a trade-off then probably. But here I don't think. Let's see, where do we? Let's say if we go to the last. So the node varying has less parameters per communication round, right? So indeed you could. So this one will get closer to the red one if you would plot it versus the number of parameters, or the times that the parameter is being used. Let's say.
Right.
In every communication round, you could say that the node varying is using less parameters than the edge varying. So then it would come close, but still, in the end, this is the time, right? So if you look at convergence time, then it's the number of communication rounds that is important.
Got it.
Number of parameters that becomes important, I think, in data-driven cases.
Okay, thank you.
And that's why this edge varying. So the use of edge varying in these graphical neural networks, so you need a lot of training data. So very often they're only used in a hybrid fashion, where you only use these edge weights on some of the nodes, some of the important nodes, but all the other ones you use one parameter and not a different parameter on all the edges. So I think Alvin Isufi has been looking at that, and so he's proposing this hybrid form because that gives you a good balance between number of parameters and amount of training data.
Okay, perfect. So let's see.
So I was either very clear or very unclear. I don't know which one of the two, but
so
probably it was too simple for everybody.
So one question that came up. So I'm giving you the hard ones, right? Because that with the interesting one. So one question that we had at some point where I discussed this with some of the students had to do with in designing the edge varying filters. You're constrained by the support of this underlying graph, right? So and then one could take this design a step further and then tell you, okay, what if I would give you certain budgets of edges that you can incorporate, upon which then you can design, right? So you can design weights and stuff like that.
Yeah.
What would be a good way to think about even attacking a problem like that? I don't know if you guys thought about it.
Yeah, so what I mentioned in this hybrid form, so I think Alvin was just using either the degree of the nodes to select where he puts these edge varying weights or centrality, and so he was using these type of measures, but it was more out of intuition.
Yeah.
So probably you could maybe, if you add a sparsifying, if you add some kind of you would like to learn this, of course, right? So from the data that tells you where you could use the classical, so the same weights for all the nodes or not, but so that would mean that you have to add additional constraints somewhere during your learning, or some kind of group sparsity that says, okay, do I want to group certain coefficients together or not?
Right. Yeah. Okay, I see. Yeah, maybe doing
so you can start with the full block with the edge varying setup, but then you say, okay, look, I want to somehow also put a budget on how many different values I have in my coefficients. So, and that is some kind of a group sparsity constraint then, right?
Right.
For a certain matrix. So that could be a way to have, if you add that constraint, to learn by yourself what are the places where I should have different weights or similar weights.
Okay. So we got one question, which is basically that I already put someone else's question. Okay. So being 2:05, 2:06 now, and so I think this is a good point to stop. So thank you, Geert, very much for the talk. So this is recorded, so we will upload it so you guys can listen to it again, or people that didn't have a chance to join will listen it in the future. So now you have a short break, until 2:20, and then we'll jump in onto some one-on-one meetings on a different link.
And if people have questions, they're happy to. They're free to email me. So if they have any questions about the talk later on or about the video, then if they watch it later. So
awesome. Thank you very much, Geert.
Yeah.
Thank you for joining.
Yeah. Bye.